For those of you who have checked the longest lesson we had so far, which is lecture 30, the squeeze theorem, you will notice that we talked about so many things, but there are some other things that are only important because they are coming in the test, and there are other things that are important because they are coming from the exam. And also, more importantly, there are other things that are there that are so important for the next topics to come, especially when you're doing the first principle of finding a derivative. So I'm just going to list some of these things and then move forward, because today I want us to talk about continuity and make sure that we do as many examples as we can. So let's look at some of the things that are important that we talked about in the previous lesson. We said that whenever this is just a quick summary on the squeeze theorem. So basically we said that if you wanted to use the squeeze theorem, all you need to realize is that if you are given some function f of x, and you know that you want to find the limit as x approaches some value a of f of x, and you know that you can find some function h of x such that this function is always bigger than that function, and this function is always bigger than g of x in a certain interval. This function does not have to be always bigger, but as long as you are near K or close to a, if that happens, then we are fine, close to a. And if this is the case, and you know that this is happening, and the limit as x approaches a of g of x is equal to the limit as x approaches a of h of x, then because the limit of this and the limit of that are equal, then this one also must be equal to those limits here. If these limits are equal to some L, then this one must also be equal to some L. Now, what are the important things or important limits that we actually solved with the squeeze theorem that you need to know? Because if you don't know those limits, you won't survive when it comes to finding the derivative of a function using the first principle. You need to know these three limits. The first one is when we are saying the limit as x approaches 0 of sine of x divided by x. You need to know this limit because in order for you to find the derivative of sine and cos, it will come in handy. You need to know it that this one is equal to 1. And of course, to prove this whole thing, what we needed, because in order for you to prove, you need functions that are actually bounding this function f of x. So we ended up saying that whenever I have x plus 1, this is always gonna be, not really lying now. For this one, we said that whenever I have sine of x on the interval 0 less than or equal to x and x less than or equal to pi over 2, I knew that sine of x was less than or equal to the function y is equal to x, and this function was always we had this thing here, and also we used this understanding to realize that we had sine of x divided by x less than 1. And also from this was the first part that was important. The second part was we had our function y is equal to x. It was less than or equal to tan of x. And then we used this to realize that we have a sine inside divided by cosine of x. And we used these functions to actually prove this whole thing. So these are the functions that are important for you. You need to know. And when you are using 0 is bigger than x and x is bigger than negative pi over 2, the inequalities were reversed, but these were the functions. And then from there, this is one most important limit that you need to know. The second one is the limit as x approaches 0 of cosine of x minus 1, or 1 minus cosine x divided by x. We used this limit to find out actually this limit here is just gonna be equal to a 0. So we use this limit to prove that. And now the last one is, if let's say you want to find the limit as x approaches 0 of e to the power x minus 1 all over x. You need to know these limits here, and this one we said that it is equal to 1. And to prove this limit, what we said that you can either use this function that e to the power x is always going to be less than or equal to x times e to the power x plus 1. So that was the first thing that we actually covered, that if you actually have this function, this is always going to be bigger than that, and this is always going to be bigger or equal to x plus 1. So if you can remember this whole thing, only this part, you will be able to prove that whole thing, because you're going to subtract 1 throughout, divide by x throughout, and of course you're going to use a certain interval if x is bigger than 0, because when you're dividing by something bigger than 0, inequalities don't change. But when you're dividing by something less than 0, inequalities change. You need to also consider that. You can use this one. I use it because most of the time this is what usually makes some sense, and also this function here is easy to derive these functions, why they they are there. And then another thing is that because I have e of x, I know that this one here is easy for a student to remember, that oh, I have e, then I must multiply this x here by this e of x, right? And then I need to add that one here so that I can end up subtracting it to get this whole thing. So this one here is that one, and this x here is that x. The same thing here, this x here is this x, and that one is this one here. But others don't prefer to use this choice of, you can find other functions. I'm just gonna give you, let's say, 3 choices, but there are more, because this thing, the only thing that you need to do, you need to find these functions that are sitting here that have the same limit, so that they can squeeze it to the same limit. So this one you can also have x plus 1 less than or equal to e to the power x, and then this is less than or equal to x squared plus x plus 1. You can use this choice of functions. No one is preventing you from that. You can use this choice of actually functions. So if you use this, you're still gonna get the same answer that you actually need. You're still gonna be able to prove that. Or you can use x plus 1 less than or equal to e to the power x less than or equal to 1 divided by 1 minus x. I know that in class this is the one that I used, but more on the notes I used this one, and these two. I want you to get familiar. That's why I'm doing this, to get familiar in the choice of functions. How do you end up choosing those functions? So you need to know this. You also need to know this limit, because if you don't know this limit, you will be struggling with some of the things that you'll be doing when it comes to finding derivative using the first principle. Just to mention it, that formula that says that the limit as h approaches 0 of f of x plus h minus f of x all over some h here. So if you look into this particular limit here, in order for you to solve most of the problems that are involving trigonometry and also exponential functions, this one usually, these limits usually come in so handy. So you need to remember them, that this is 1, that one is 1, this one is 0. Just have that. So that's the part that I want you to mention, so that you can prepare yourself for what is coming. Let's talk about continuity now. Continuity. This is what I want us to actually look at today. So what is actually continuity? When do we say a function is continuous? That's what I want you to first get a close. So let's first talk about continuity at a point. At a point. So that's the first thing that I want us to talk about. A function. So whenever we're talking about continuity, what we want to study is the continuity of a function. So if something is really not a function, then there is no point talking about the continuity there. So first, we must have a function f of x is said to be continuous at a point x is equal to a. If these three things happen, if number one, right, f of x must be defined, right? F of x must be defined, and f of x must be defined at point A. In other words, we must have some f of a. If f of a must be equal to some value, let me write it here. F of a must be defined and be equal to some value L. This L can be 5, it can be 10. So what is important is that this A here must be in the domain of this f of x, so that when I'm plugging A, I get a value of that function. That's the first thing that needs to happen. The second thing that needs to happen here is that the limit as x approaches A, right, of f of x, it must exist. So this limit here must exist. What do we mean by saying it must exist? We are saying that the limit as x approaches a on the right of f of x, it must be equal to the limit as x approaches a on the left of f of x. So if these two things are equal, then this limit exists. So that's condition number 2. Now the last condition, which is the third, is saying that the limit as x approaches a on both sides of f of x must be equal to the same value that you get when you're plugging in f of a. So this must be the same as f of a, which is just L. So whatever this limit must be, I must be able to just plug in this a and get that. So if I have a function such that when I'm plugging a, it is defined and the limit exists to be the same value as that value, then we say the function is continuous at that particular point. That's what you need to know about continuity, and this is the definition of continuity. Let me make one example here. Just make an example here. Right. So when we are saying, suppose that I have my f of x is equal to x plus 1. Right. The question is f of x continuous at x is equal to, let me say, 3? That would be the question. Is this function continuous at this value x is equal to 3? So what you need to find out is what will be, first, the first condition is f of 3. What is the value of f of 3? So if I'm taking f of 3 in the value of x, I'm plugging in a 3 there. So I will end up having 3 plus 1, which is just a 4. Now, second condition is we wanted to find the limit as x approaches 3. So what is the limit as x approaches 3 on both sides? Right. So the first thing that you need to do here, we want to find the limit of f of x, which is just the same as the limit as x approaches 3 of x plus a 1. And if you look carefully on this particular example here, you will find out that if I am plugging in a 3, I get some value, so that value must be the limit. So it's going to be, I'm going to take this and plug it there, I'll get 3 plus 1, which is equal to 4. Now you can conclude, because this limit, by finding the limit to be 4, which means the limit exists. So this one is actually dealing with condition number 2 and condition number 3, so at the same time. So you can just say, therefore the limit as x approaches 3 of f of x is also the same as f of 3, which is equal to 4. Therefore f is continuous at that point. It's not that hard. This thing is not that hard. It's continuous at x is equal to 3. So it is continuous at that particular point. Let me take another example so that I can move to other things. Let me take another example here. Is the function f of x equal to, I'm just gonna give you this, no, I don't want to do this. I have x squared minus 9 over x minus a2. No, a3. Now, if you look into this function is just the same as x plus 3 and x minus 3 all over x minus a 3. Now, to find, is this function f of x, which is equal to that, continuous? So that's the question you want to answer. The first thing that you need, continuous at x is equal to 3. Right. The first thing that you need to find out is, what is the value of f of 3? So if I were to plug in here x is equal to 3, here I would get something, here I will get a 0, but here I will get a 0. So f of 3, we know that f of 3 is undefined in this case, undefined. Right, so this one, f is undefined. Let's go back here. Condition number 1, we want f of x to be defined and be equal to some value L. So here we are actually getting f of 3 is undefined. So because this one condition is not satisfied, you don't have to check other conditions, because this one condition is not satisfied. You can just say f of x is undefined, therefore f is discontinuous. It is discontinuous at x is equal to 3. That's what you need to find. You don't have to end up looking for the limit. If the function is not defined at that point, then it cannot be continuous, as long as it is not defined. You only check the other two conditions if the function is defined and is equal to some value. Now, let us talk about now continuity at the interval. I'm just gonna try and make this as much easier as it can be. Some people have different ways of saying this whole thing, but I want us to look at just the definition of continuity at the point is that this must be satisfied, this one must be satisfied, and that must be satisfied. If this one alone is not satisfied, then if you can find that this one is not satisfied, then the function is not continuous or discontinuous. There's a point of discontinuity at that point. And also, if this one is not satisfied, then the function is not, as long as one of these conditions is not satisfied, then the function is not continuous. So let's look now at continuity on the interval. So I want us to talk about the continuity on the interval. I'm gonna say x so that you know that this interval is talking about x. I have a here and then I have b. What this actually means is that I'm just gonna give you a simplest definition of this. The first thing that must happen is that this interval must be continuity on the interval. This interval here must be in the domain of the function. That's the first thing. The second thing is f of this, if I take this value and I plug it in the function, it should be the same as the right limit. And also this one here, it must also be the same thing should also happen. Let me write what I'm saying here. First of all, continuity on the interval. I'm gonna say this: f is continuous on the interval a b if only these things happen. So if I take the limit, I want you to take note of this. If I take the limit as x approaches a, this is the smallest value this limit, this interval can have. So if I take this limit, but to approach this point, I have to approach it on the right, because this is the smallest value there is, and below this point we don't have a function. So I'm going to approach this on the right. So I'm going to say the limit as x approaches a on the right of f of x, it must be equal to f of a. That's condition number one for this thing on this interval. And then secondly, the second thing that should happen is this: the limit as x approaches b, which is this value here on the left of f of x, must be equal to f of b. That's what is important. The third one is this: for every point k, right, for every point k, where k is on the interval ab. Let's take note of this. Now I'm not using the square brackets because I've already covered what is on the square brackets here. So the endpoints I've already talked about. Now I want us to talk about everything that is in between these 2 points, right? So every time I pick a point in between there, I get the limit as x approaches that to k here on both sides of f of x. This is the same as f of k. If these three conditions can be satisfied, then we know that this particular function on f on this interval, it is continuous. This one here, we usually say it is this one. The meaning of this thing is just simply saying that this one is continuity. This is a continuity on the right, so it is a continuity on the right of a, so, or the end point continuity. And also this one is also the continuity on the left, so I can just say this on the left of a. So that's what this is actually saying. Now this one here, we are actually looking at every particular point on that interval. So that's what this thing is actually saying, that if these three conditions can be satisfied, then you know that f is continuous on that particular interval. So that's the difference between continuity and the point, because continuity on the point is only talking about number 3, but continuity we also have to check the 2 intervals. Let us try and take an example. I'm going to take one example here, but this example, let's hope that this example is going to be more fruitful. I'm going to have this, and I'm gonna have this, and then we're gonna take some more problems, because this is just some little bit of theory behind, but it's not that dense. It's just taking some few things on the top. Suppose I have this point here. Okay, suppose I have this function here which is going nicely like this. I have this point here which is going nicely like this, and I also have this point here. Where am I gonna put that point? Okay, I also have, I'm gonna extend this so that it is here, and then on top of that I'm gonna remove this. I'm also having a nice point here, which is going all the way like this, and then this is going all the way like this, and here I have something here, and then I also have something here which is going all the way like this, and then it keeps going like that, and then at this point here I'm gonna say that I have a 1. This is not a 1, it's an A. I have 1 here, I have 5 here, I have 6 here, I have 7 there, right? So at this point here I want to say I have a 1, and then at this point here I want to say I have a 5, and at this point here I want to say I have an 8, and at this point here I want to say I have a 9. So that's what I want us to talk about now. So if you look carefully here, I want this one to be defined here, and here I want to have a hole, and then here I wanted to have another hole, and then here I wanted to and here I wanted to end up having another hole here, and then we have that. So basically I want us to find point of discontinuities, or a point whereby the function is not continuous. Let me first start with this here. This whole thing is characterized by f, so this function is characterized by f. Suppose the question is saying that is the function f continuous on the intervals. So the first interval is going to be, I'm going to talk about 1, 5, right? And then this is going to be the first one, and then the second one I will be talking about this is going to be the second one. I'm going to talk about the interval between 5 and 6. I'm going to talk about the interval between 5 and 6. So the second interval is going to be 5 to 6, and then the third interval is going to be, I think those are the two. And then another question will be is the function f continuous at the points. So I want to talk about the points when x is equal to 1, number 2, the x is equal to 2, number 3, x is equal to 5, number 4, x is equal to 6. So I'm gonna use these points here to see what is basically happening here. So to find is this function continuous on this particular interval, the first thing that you need to find out here is that condition number 1 was, is the limit as x approaches, this initial point here is 1, so we have this one here, but whenever I'm dealing with this initial point, I am approaching it on the right because there is nothing this side. So the only thing I will hit a function is when I pick a point on the right. That is why we usually check only the right, the positive, because on the left there is nothing. So I wanted to find the limit of this f of x as x approaches this one, but on the right. So if I were to pick a point just after 1, let's say the point is going to be 1,000000000000000000001. That point here, when I'm plugging it on the calculator will see that that's just 1. So when you're going to the output of the function, it's going to be the same output that you are getting. According to the calculator, it's going to be the same output because the value that is so close to this point on the function is that 1 here. So this one is going to be this limit here is going to be 1. But if you look now at f of 1, what is f of 1? So I'm looking at f of 1. If I were to take 1 and plug it in the function, what is the output? So the output when x is equal to 1 is still 1. So this one is the same as f of 1. So we can say that condition 1 is satisfied because when I'm plugging in a 1 here, I end up getting the same value that I get for the limit as I'm approaching 1 on the left. And then the second thing that I need to find out is the limit as x approaches 5. But now when I'm approaching 5, if I'm approaching 5 on this interval, when I'm saying 5 comma something, I'm outside this interval. So to get something close to 5, I need to be on the left of 5. Hence we end up having a minus on top to say that we're on the left of 5 of f of x. So if let's say now I pick a value just on the left of this 5 and go all the way up, the output that is so close to that value is going to be this 5 here. So this one is going to be 5. But if you also look on this function here, whenever I'm plugging 5 in the function, the output is going to be the 5 there. So this one is still the same as f of 5. So condition 1 is satisfied, condition 2 is satisfied. Now we want to find out what will be the third condition. The third condition is this. What we usually do is say, we just usually say let a, so we let this a to be inside this interval. Take note of these two brackets here. So if my a is in between these 2 points, in other words, my a is just somewhere in between. So I pick my a here and then I have some value there and the output of this function here, because if you really look into this is a straight line, and in this particular point here you will find out that we have a function here. So I'm just gonna call that that value L here. So if now I am actually looking at let a, then if I'm looking at f of a here, what is the output of the function when x is equal to a? So this a here, as I'm going to the function, the output is going to be some value L. You can choose a different alphabet, but the variable that I chose is going to be L. We have that. But now, if you look at the limit as x approaches a on both sides of f of x, what will be the value of that? So you come to the function. If I pick a value so close to a and I go all the way up, the function, I'm going to hit a value that is so close to this value. What is that value that I'm so close at? Is going to be L. And if I pick a value on the left of this a and I go all the way up to this point here, you will find out that actually the value that is so close to it is going to be this L. So in this particular case here, you'll find out that this limit as I'm approaching a, this is going to be some L, which is the same as f of a. So this condition is also satisfied. Another way to look into this, when I'm drawing this function, I can continue to draw it from this point up to that point without lifting my hand. So in between these points, this function is just continuous. You get what I mean? So you can say that or write it in this particular format. Therefore, because condition 1 is satisfied, condition 2 is satisfied, condition 3 is satisfied, you can just say therefore f is continuous on the interval. We have 1 up to 5, right? So it is continuous because this is satisfied, and this one is satisfied. Now let us look at this interval now from 5 to 6. So I'm moving from this point to that point. Okay. Now, the first thing that you need to do to find out if the function is actually this one here is actually defined, it's actually continuous. So the first thing, you want to make sure that the function is defined at that point. Now, if I look at f of 5, what is the output of f of 5? Now, looking at this 5 here, this part is shaded, which means that the output is here. There is a hole here, which means there is nothing. So the output of this position is this one here. So f of 5 is this point here, which is just 5. So I have my f of 5. Remember, this 5 I'm talking about is this one. So f of 5 is the same as 5. Now, I want us to look at now the limit. The limit as x approaches 5, but in order for me to approach 5 in this interval, because 5 is the smallest point, is the smallest value in this interval. So the only way I can approach 5 is when I'm on the right of 5. So when I'm saying 5 comma something, I will be in this interval. But on the left of 5, I'm gonna get 4 comma something, and 4 comma something is not part of this interval here. So I cannot pick something on the left. I can only pick something on the right. Now, I am picking a value that is on the right of 5 of f of x. Now, we are going to a function to check where is that value in the function. So if I pick a value on the right of 5, I am not going to hit this function. I'm going to hit there in that function. So any value that is on the right of 5 is going to be hitting somewhere there close to this point, and the output of that point is actually going to be an 8. So the limit or the value, if I pick a value so close to 5, I will end up getting an 8. And this 8 here is not equal to 5, which is the same as f of 5. Therefore, because this condition alone is not satisfied, you can conclude right away that f of x is not continuous on the interval 5 to 6, because the endpoints, the limit on the endpoints is not the same as the function. So that's what I wanted you to see the difference, that to be continuous on this throughout this interval, whenever I'm picking f of x, then f of x is I'm going to be able to satisfy these three conditions. But when one of these conditions is not satisfied, therefore you are done. It's not continuous. That's what is important. I am not saying that whenever you are given interval, you must always be having the square bracket. Sometimes someone might just say that, is this function continuous on this interval 5 to 6? So in order for you to solve this, one thing that you have to realize is what is the meaning of these open brackets. These are open brackets, which means that a value that is inside here, 5 is not part of this interval, because 5, we don't have square brackets. The reason here we have a 5 is because we have the brackets, the square brackets, but here 5 is not part of this interval. What we actually mean on the graph here, we actually mean that values that are here are the one that we're actually talking about. And you can see that starting from this point throughout up to that point, I can draw the function without lifting my pen up. So the function here is just continuous, but you can check, because that thing is saying that first find the limit. So what you are actually going to do here, you only gonna find out, in this case, when this interval, when we're using the square, the open brackets, you're gonna have to just find what is the limit as x approaches 5 on just the right of f of x, and you will find out that the limit is just gonna be 8. And every time you pick a value, let's say I pick a value that is on the right of 5, I'm gonna say that value is going to be f of a. If I pick a value where a, I'm gonna say here, where a is an element of that interval, 5 up to 6, you will find out that actually if this value is so close to this 5, this is still you're gonna end up getting an 8, because we have a flat a straight constant function here. So whenever I'm picking a value here that is so close to this, I'm gonna get an 8, and whenever I'm picking a value here so close to the endpoints, I will end up getting an 8, and whenever I'm picking a value in the middle, I will end up getting this. And the same thing is going to be the same as the limit as x approaches 6 on the left of f of x, because when I'm picking 8, a value on the left, I'm still gonna get the 8. So for this particular curve, for this particular interval, we can say that f is continuous. I hope you get the difference here, continuous, because what is actually important here is not the square brackets, is what is happening in this interval. Can I draw the whole curve within this interval without lifting my pen? That's the meaning. But if I am considering square brackets, I am also considering this part here and that part, but I cannot place my pen here because there's nothing here, so I can't even start to place place my pen so that I can draw to this hand. Even if I start here, there's nothing here. I cannot go and finish this whole thing because there's nothing there. So when I have square brackets, I had a problem of drawing it. But when I'm having open brackets are saying don't include that value, don't include that value, so start just after that value, so I can start here and go all the way until I arrive there. So it is continuous when I have the open brackets. So I hope you actually get the difference here between this. Let's look now at the endpoints, and then we talk about the point of discontinuities. We classify the point of discontinuities, and then we'll be good to go. If you look at this point here, if the function is continuous, is the function continuous at these points? The answer is, let's go at x is equal to 1, right? If you look at this point here, I'm going to try and talk about this, and maybe we'll actually get an understanding of this. Let me start with these ones that are straightforward. I have x is equal to 6. X is equal to 6. If you look at x is equal to 6 here, there is a hole here, there is a hole here, which means the function is not defined at that point because there is no shaded region there. So we can say that for this one here, I can simply say that f of 6 is not defined. Since it is not defined, therefore f is not continuous, or it is discontinuous. It's not continuous at x is equal to 6. One condition is not satisfied, so it is not continuous. Clean. So you are done with this one here. And then let's go to x is equal to 5. If you look at x is equal to 5, the function is defined, and the output of it, because we are shaded, it is shaded here. This point here, you can see that the output is going to be 5, right? When we're dealing with this, we found out actually that the limit, as I am going looking into this, you find out that the output of this function is 5. So let me just write it instead of shortcutting it. F of 5 is just equal to 5, right? But if I am looking the limit as x approaches 5, what is that limit? The limit as x approaches 5, I am going to go to the function here because I'm looking at that point here. So if I am looking at this limit here, the limit as I'm approaching 5 on the left, I can tell you that the limit as I'm approaching 5 on the left, it is going to be 5. But as I'm approaching 5 on the right, when I pick a value just on the right of 5, I'm going to hit that function there. This value is going to be 8. 8 and 5 are not the same. So we say that the limit as x approaches 5 on both directions does not exist. So the limit does not exist, therefore it's not the same as 5. Hence, f is not continuous. at x is equal to 5, because the limit does not exist. So f is not continuous at that point. Limit does not exist. If it existed, then we'll be talking a different language, because the limit does not exist. The limit has to exist at the point, and then secondly, it must be equal to the function to say that this one is actually continuous at that particular point. Once you pick one thing that is not happening, then it's not continuous at that point, right? And now, bear in mind that when you are dealing with the interval, just make sure that you understand the difference, that when we are dealing with the interval, we look at the limit on one side of the endpoints. That's what is important here. But when you are looking at the continuity at the point, you want the limit to exist on both sides. I want you to get to take note of that. That for the point, you want both sides, but for the interval, for the end points of the interval, you are looking for just one side, the limit of one side to be equal to the function. Let's look at x is equal to 2. What is f of 2? Let's look at f of 2. If you go to this function here and you pick a 2 somewhere there, 2 is going to be there. So when you are going all the way up here, you will find out actually 2 is here, and this 2 here is going to be a point there. Because this one is 1 and this one is 5, I can assume that is also gonna be 2 in that particular function. So here I have f of 2, which is the same as 2. And now I want to find the limit as x approaches 2. So if you look in this region here, if I pick a point just on the left of 2 and go up there such that the difference between 2 and that point on the left is so small, the point that I will get here, it will be so close to this point such that we cannot see the difference. So that limit on the left is going to be just the same as 2. And when I'm picking a point so close to this 2 here, the output in the function here is going to be so close to that point such that I don't see the difference. Hence, the limit on both sides is going to be at 2. So in this particular case here, this one here, the limit of f of x as x approaches 2 is just the same as 2. So I have this function which is the same as this function here, as the limit. Therefore, I can conclude that f is continuous at that point. Continuous at that point, x is equal to 2. So f is continuous here. And if you look into x is equal to 1 here, I'm just going to say this in words. I want you to note this. When we're doing this here, we only looked at x is equal to 1, but on the right of 1, because there was nothing on the left, because we were dealing with the interval. So when we're dealing with the interval, we'd only focus on the right of this small value, and when we are dealing with the interval, the largest value, we usually look on the left of it. So here, if you notice, we only looked on the right, but now because we are dealing with the whole point 1 here, you can see that the limit or just on the left of 1 does not exist because there is no function there. So what you can say here on this point, the limit as x approaches 1 on the left of f of x, we know that it does not exist. So because that limit does not exist on the left of 1, you can conclude that at x is equal to 1, the function f is discontinuous, or is not continuous at that point. I know and I am aware that there are most people who want to actually mix these two things, and they want to say that it is continuous at 1. We can say that it is continuous because of one reason. If we consider 1 as a point, then there is nothing on the left of 1 because we want the limit on both sides to actually exist, but here we don't have the limit on the left. So 1 as a point the limit does not exist. But when we are dealing with the interval, because we're only gonna approach it on one side, then we find out that the limit existed and it was equal to 1. I hope you can see the difference here, because I don't want you to get mixed in this whole thing and just assume that because 1 was part of that interval, and when we're looking one-sided limit or the end points continue, the continuity at the end points, you find out that now you are actually having some confusion there, that no, it was continuous, has to be no. We are looking at x is equal to 1 as a point here, which means both on the left and both on the right. Now let's talk about points of discontinuity and classification of those points, and then take some serious examples and see if we can move forward. This is was just an explanation on what is happening in theory wise, and then we're just gonna take some examples here, and then we can look at some point. Just a summary, just a little bit or a quick summary, is that a function f is continuous on its domain. So the domain, we consider it as an interval, so the endpoints here are actually considered to be part of the interval, so we approach them on the ends. So if, let's say, now we are talking about a polynomial is continuous everywhere. So it is continuous everywhere because I can draw it from a polynomial without lifting my hand. So I can draw it and continue to draw it without lifting my hand. And then I have power functions. Power function is continuous in its domain. And also another functions, this is just, I just want to give you this quick analysis, that every single function, it is continuous in its domain, right? But the issue now, when I'm talking about this, I am not talking about the piecewise function. I am talking about one function that have a single domain. So it is continuous in that domain, right? So it must be continuous in its domain. And also on the same time, if we have piecewise function, we know that that function is not going to be continuous everywhere. And also if you have points that have let's say I have a function like this, f of x is equal to suppose that my f of x is just equal to t of x, where t of x, let's say maybe this t of x is going to be some series a raised to x. Suppose I have this. When I'm trying to write this like this, I'm just saying that this function is a sequence of numbers. Like if, let's say, here I'm plugging in a 2, the first one, I'm just gonna say, okay, suppose this first one is I'm gonna start at 1, so I'm gonna say 2, and then 4, and then 8, and then 16, and so forth. If you look into these points here, suppose I have a sequence of numbers, and I have a function that is characterizing a sequence of numbers. So even though here our x here, its domain x is going to be, let's say, 1, 2, and so forth up to some n, right? You will find out that this one here, in its domain, I have only points. I don't have intervals. So when I have an output that is just a dot in the function, I know that there won't be any limit on the left because there's nothing on the left of the point, and also there's nothing on the right of the point. So this function here is discontinuous everywhere because we don't have a limit when we are going on the left and also on the right of that particular point. So we are only talking about functions that are actually having a domain that does not have single points. It just have some intervals. So all these functions can actually be continuous in their domain as long as we don't have points. Now, having this nice summary that look at the domain, and as long as the point is within that domain, you must know that that function is continuous at that point. That's what is important here. So if you look into this function here, you will find out that looking at the domain of f, any point that is in between here, it is part of the domain. So here I know that the function is called, this function is continuous everywhere within this interval, and any point that is in between here, because anything that is in between is going to be part of the domain. So that is, this function is going to be continuous if I pick any interval that is in between these 2 points. If I pick any interval that is between, then the function is going to be continuous everywhere. And here at 7, you can see that the function is not continuous at all, because the limit as I am approaching this function here is the same as the limit as I'm approaching it on the right, but the function is not defined at that point. As long as the function is not defined at that point, it is not continuous. So look at the domain. That's also one thing that is important. Now, point of discontinuities. Point of discontinuities. So if we are looking at the points of discontinuities, I want us to be able to try to actually classify them. If, let's say, I have a function, this is my function, and my function is going all the way, and here I have a hole, and then the function continues nicely, and then that point here, you can see that the function is not defined. If the function is not defined, then it is not continuous. So this is a point of discontinuity, right? Because the function is not defined there. So this one here, because we have a hole, we call this one a removable discontinuity, right? And the second one will be something like this. I have my function, there is a hole there, I continue this way, but this function is defined somewhere there. Suppose this is my a. If you look, this is f. This function, yes, it's not defined there, but this function is defined here, which means when x is equal to a, the function is defined to be having that value there. So the function is defined, but this output is not the same as the limit, because the limit will be actually looking for the output that is close to that value, which is way above this value. But what is important here is that I have this hole here, and if I were to push this point all the way here, I will be able to redefine this, or I will be able to remove this discontinuity. So this discontinuity is also called removable discontinuity. So removable discontinuity, you have a hole, and the function is either not defined at all, but we just have a hole, or we have a hole and the function is defined to have a dot somewhere else, but the function is approaching on both sides. So we have this. So we have a removable discontinuity. A removable discontinuity is this. The reason behind this is because of this. You only get a hole if you have a function such that something like this. So if we had this function, I have x minus 3. This function is same as x minus 3, x plus 3 and x minus 3, and then divide by x minus 3. And we know that this function, we don't want x to be equal to a 3. If I would redefine my function, because this one here and that one, they cancel out. So if I were to redefine my function here to be equal to 5 when x is equal to 3, I will be able to remove this discontinuity. In other words, if I were to cancel out the common factor, I would be able to remove that discontinuity. Hence, that discontinuity is called removable discontinuity. Let's also look at another type of discontinuity here. If, let's say, I have a function like this, and I know that at this particular point here, the function is either going this way, this side, or is going that way, that side, or I have a function such that this side we are going that way and this side we are going that way, or I have another function here such that at close to this point here, the function is either going this side and the other one is going that side, or I have another thing here at this point here. The point can either be that side or anywhere, but close to a certain point A here, the function is going this way and the other one is going that way. Or I have this here, I have a point here A, and the function is going all the way and then it is defined there, but when I'm approaching it this side, the function does not touch that point A here. So we say that at this point here we have an infinite discontinuity. So this discontinuity here is happening at infinity. Others are usually calling this, we have a discontinuity at infinite or infinite. Yeah, it's just infinite discontinuity because at this value the function is keep continuing approaching it until we arrive at infinity. So at infinity, that output infinity here, these functions are assumed to be touching to each other somewhere at infinity. That's why this one is called infinite discontinuity. The same thing here, if I were to draw this function, there is some chance that maybe at infinity I end up touching something, and then touching that function I end up starting this side. This one is also said infinite discontinuity. And also this one here, because this one is going all the way up to infinity, it keeps going all the way. This is also infinite discontinuity, even though this one is going on negative infinity and this one is going to positive infinity. Everything that revolves around something infinity, those discontinuities, we call them infinite discontinuity. The last one now, we usually call it something like this. So if I have a function and this function here is going all the way to some value, and then somewhere else now it goes like this, or yeah, and then looking in this point, moving from this point to that point, actually you can see that from here I have to step up or I have to jump to get to that function here. So this one here, looking at this particular point, is usually called the jump discontinuity, or someone might say it's a step because we end up jumping. Yeah, the step is not usually that much more making sense, but it is I think the jump is actually the one that is good. And also, if you look into this one here, this one is usually confusing so many people because I have something that is moving like this and then it goes like that. If let's say you look into this point here, you can see that from this point A here, I have infinitely many outputs at this point. So this is not even a function to begin with. So classifying this whole thing does not even make sense because we wanted to talk about point of discontinuities when we are dealing with a function. This is not a function because it's actually having so many outputs. If I go to A have that output, A have that output, have that output. So this is not even a function, so let's not bother with it. Let's only bother about this, that we actually have a jump discontinuity, and then here we have infinite discontinuity when we are around a point that is actually an asymptote, and then here we have a removable discontinuity. But now if you were to actually classify this, you are in a point of actually, hey, classify this. All you need to just say here, someone with some sense will actually understand what you are trying to say, that because the limit on the left here is not going to be the same as the limit on the right, and even the function here have so many outputs, you can just say that this one is a step step up or step down, or you can just say step discontinuity. So that's how you can classify points of discontinuity. Now, every single time, I want you to take note of this. If, let's say, you are falling in this particular category here, I want you to know that in matter of fact here, this is an asymptote. As long as you are around an asymptote, you are actually having infinite discontinuity. That's what I want you to see. And if you look into this function here, you can see that at this point here at 5, we have a jump discontinuity, and at point x is equal to 6, we also have a jump discontinuity because we are jumping from this function to that function. And also here, even though the function is defined here, we have a jump discontinuity. Even though the function here is not defined at all, we have a jump discontinuity. And x at x is equal to 7, we actually have an infinite discontinuity. I hope this makes a lot of sense, because this is what is important. I want you to know these things. And now let's look at the realistic problems now on how you can actually solve these particular problems. I want to look for tutorial 6. Where's tutorial 6 here? I want to look at tutorial 6. Do I have tutorial 6 here? Seems I don't have one. I don't have tutorial 6. Okay, let me do this. Let's look at this tutorial 6 here, and the questions. These are exam type question. Evaluate, use continuity. I'm just gonna highlight some of these. I don't know why this thing is not actually showing. I want to make sure that at least you get this continuity thing. I have tutorial 6. Yeah, let's hope now it's going to open up. So let me clear this, open it again, new window, and then I want to anoint this tutorial 6. Why is it not showing up? I have tutorial 6. Yeah, tutorial 6. So I want us to look at this one here. Find the following limits if they exist. Let's leave that one. Consider the definition of continuity at a point to show that the following functions are continuous at the given point. So if you look into this one here, I'm going to choose that, and I'm going to choose, I want to use a pencil here. So I want us to look into these questions here. Use the definition of continuity at a point to show that the following functions are continuous at the given point. What we actually mean by this is this. What is the domain of this particular function? Right. So the first thing that you need to find is the domain of this function here. So the domain is always going to be x is an element of real numbers such that something happens. So x to the power 4, I can plug in a negative value here, I can plug in a positive value here. So this one is defined everywhere. So for this one, x is an element of real numbers, and this one here at x, I can plug in a positive value and negative value. I'm still sorted, so it can take any value with this one. And when it comes to this function here, because this one here is an odd number, I can plug in anything here. It can be positive, it can be negative, it doesn't matter. So this one here, because of that value here, which is an odd number, so the domain of this function is x is an element of real numbers. So when they are saying use definition of continuity, they want you to first find the domain of this function. Check this point here. If you look at this point here, so you write the domain is this, and x is equal to 2 is in the domain. I can say it is in the domain. I can say this one is an element of real numbers. So it is a real number, this 2. Therefore, because this one is inside this domain, then f is continuous. at x is equal to 2. You are done. Find the domain, and then if the domain, you got it, and this point is part of the domain, then f has to be continuous at that particular point. The same thing here, I can plug in anything, therefore this function is continuous at that point because x is also a real number. X is equal to -1 is a real number, so I can plug in real numbers here, so I am still sorted, so we are fine. And then let's go now to this point, which are juicy ones. Here you need to find the domain and then check this if is it in the domain. If it is in the domain, then that function is continuous at that point. Let's look at these ones now. Explain why the following functions are discontinuous at the given point. So if you look into this function here, we want to find out, is this function continuous at this point here? If I were to plug in here, remember that 0 is included here. So since 0 is included, therefore this function is defined when x is equal to 0. So don't go there because they're already telling you it is discontinuous. So to prove if something is continuous at a point, you need to first make sure that it is defined. Secondly, the function is actually equal to the limit, both the left and right limits. Now, if you look at the limit for this this one here, let me draw a line here and also draw another line here, and then this one will also be something else. Look at the limit as x approaches 0 on the left of f of x. I want you to see this. If I pick a value on the left of 0, that value is going to be negative. In other words, we're going to be here. So the negative value, if I plug it here, I will end up getting a value in this particular function. So if I plug in a 0 here, I will end up getting the limit as x approaches 0 on the left of e to the power x, because this is the function that is on the left of 0. Now, this function is continuous everywhere, so I plug in to get e to the power 0, which is just equal to 1. Now, if I am looking at the limit as x approaches 0 on the right of f of x, what am I actually getting? On the right of 0, I get a positive value. Everything that is on the right of 0 is positive. So I go to that function that is on the right of 0. This is for positive, so this function on the right of 0, we have that. So I will end up having the limit as x approaches 0 on the right of x squared. X squared is continuous everywhere, so if I plug in a 0 here, I will get 0 squared, which is 0. 0 and 0 are not the same, so this one is not equal to that. That is why this function is discontinuous at this point, right? So I end up having this nice thing here. This phone was actually disturbing, but what is important here is that we know that to actually find out if the function is continuous at that point, it must be defined, and then secondly, the left and right limits needs to be equal, and if they are equal, they must be equal to the output of the function at that particular point. Now, let's look now at this particular example, why the function is actually not continuous. Let's first look at when x is equal to 1, what is f of x? X is equal to 1 is not part of this domain. X is equal to 1 is part of this domain, which means f of 1 is actually this. This is the output. So actually now I have f of 1 is equal to 1, because when I'm plugging this x is equal to 1 here, I end up getting a 1. So that's why we have a 1 here. That's fine. Now, let us look at the limit as x approaches 1 on the left of f of x, right? F of x, if I am picking a value that is on the left of 1, take note that x is not equal to 1, but it's just on the left. So because if I pick a value on the left, then I know that this is not the left of 1, this is at 1. So at the left of 1, I will end up having that particular function there. And then secondly, if I am picking a value on the right of 1, then the value that I will get, x is on the right of 1, this is x is equal to 1, not on the right of 1. So x is equal to 1, x is equal to some value on the right of 1 will fall here. Hence now, for this particular function, we know that the limit as x approaches 0 of this f of x is going to be, I have an x here, I have x squared minus x all over x squared minus 1. So if you look into this here, we can always factorize, because if I'm plugging in a 1 here, I will get 1 minus 1, which is 0. And then if I'm plugging a 1 here, I'll get a 1 minus 1, which is 0. So I have 0 over 0. To solve that limit, I need to factorize. And now the common factor here is x. I have x, I have x. So I take x out. And then once I take x out now, I will end up having a 1x remaining. So I will end up having x there minus. If I take this x out, I will end up having a 1 here. And then I divide here. And then to factorize this whole thing, this is a perfect square. So I'll end up having x plus 1 and x minus 1. Because I have a 0 over 0, I need to cancel this out. And then I will end up having the limit as x approaches 1 of x divided by x plus a 1. So if I'm plugging in a 1 here, I will end up having 1 divided by 1 plus 1, which is 1 over 2. So this 1 over 2 is not equal to f of 1, which was equal to 1. That is why this function is not continuous at x is equal to 1. That's how you reason. Explain why? It's because the limit as x approaches 1 is not the same as the output of the function. The limit is half, the function is 1, so they are not the same. You don't say that, hey, we're so close by half. No. As long as these two things are not the same, it is discontinuous. Let's look at this one here. And of course here you can say that I want to find out what is happening at 0. So this one here is saying when x is less than 0, which means when x is negative. So first of all, if I'm looking at the limit as x approaches 0 on the left of f of x, you can see that on the left of 0, I'm actually going to have a negative value. So a negative value is only contained in this interval here. So the interval here is just saying that, okay, this function here is going to be a cosine of x. So if I take this 0 and I plug it inside here, what is cosine of 0? It is just 1. So on the left, I get a 1. And if you look, let's say, on the right of the limit as x approaches 0 on the right of f of x, on the right, I mean of the limit of f of x on the right of 0, on the right of x is equal to 0. What is happening? Just on the right of 0, the value that I will get on the right of 0 is going to be positive. This one is characterizing the positive, which means now my f of x is going to be this function here, which is 1 minus x squared. So this function here, when I'm plugging in a 0, I will end up getting a 1 minus 0, which is just a 1. So 1 minus 0 or just a 1. So the limit as x approaches 0, because these two are equal of f of x, I know that it is equal to 1. So one of the condition is satisfied. F of x or f of 0, so when x is equal to 0, this function is defined. So x is equal to 0 is this, so the output is 0. The function is defined, so it is satisfied. But the issue now that I have, the limit as x approaches 0 of f of x is equal to 1, which is not equal to 0, which is equal to f of 0. So that's the problem here. That is why this one is not continuous, it's discontinuous at that point. It's because of this particular thing here. The limit and the function are not the same. That is why this one is not actually continuous. I hope this makes sense. Using the continuity to use continuity to evaluate the following functions. Of course, this one you do the same thing here. What is the domain of this whole function? X must be greater or equal to 0 for this one to be defined. And also, if this one is defined, adding a 5, this one will also be defined. So 4 is bigger than 0, so I can plug in a 4. So because of this, let me write this thing down. The domain of this function here, the domain, I'm just going to call it df, x must be greater than or equal to 0 for this part to be defined. But once this one is defined, this whole thing is going to be defined. And 4 is an element of this df. So 4 is inside this domain because 4 is greater than 0. So it is part of this domain. Since 4 is part of this domain, then the limit of this particular function, you can just get it by just plugging in. So this one is just saying this limit as x approaches 4 of 5 plus square root x divided by square root of x plus 5 is just gonna be 5 plus square root of 4 divided by square root of 4 plus 5, which is just some value here. 5 plus 2, which is 7, divided by square root of 9, which is 3. So this limit here, you get it by plugging in because this value is in the domain. So when the question is saying use continuity, the domain, you need to talk about the domain. And then secondly, this value here, which is this one that we're approaching, must be inside the domain. That's what you need to do to talk about to use continuity. To use continuity evaluate limits. Domain and that. That's what is important. And then what is the domain of this function? This one, x is an element of real numbers, but the domain of this, x is an element of real numbers, but x cannot be equal to 2. 1 is not equal to 2, it is inside the domain. So to get this limit, you just plug in 1 and then you get 2 minus 1, which is just e. So that's the value of the limit. First talk about the domain, and then if this value is inside the domain, then plug in. That's what is important. The same thing for this one here. Now consider the piecewise function. I have this, on which interval f is continuous and why. At what points is f of x discontinuous? Provide valid mathematical justification. I will leave this one as your homework. Try and do it honestly and see what you are actually getting. And also number 10, I will leave it as a homework for you. Try and see what you are actually getting using continuity. I am only gonna do this one here, which is number 9, and then we can call it a day. Find the values of k, where k is a real number, that makes this function continuous at x is equal to 2. What do we really need for the function to actually be continuous? The first thing that I want my f of 2 to be equal to the limit as x approaches 2 of f of x. That's what I want. This is the condition that is so powerful. This must exist and this one must exist and they must be equal. That's what we want. What is f of 2? When x is equal to 2, looking into this domain, x cannot be equal to 2. We want values that are less than 2. Looking into this one, we have greater or equal, which means x is equal to 2 is contained here. So f of 2 is going to be equal to 2 raised to 3 minus k times 2, which is the same as I have 8 minus 2 times k. That's f of 2. And now, if I were to take a limit just on the right of 2, that value will be plugged in here. I will get the same thing. But if I were to pick something on the left, I also want the limit as x approaches 2 on the left of f of x. So if I'm picking a value just on the left of 2, it's going to be 1 comma something. 1 comma something is less than 2, so it falls under here. So I have to deal with this part here. So the limit of f of x is going to be the same as the limit as x approaches 2 on the left of k times x squared plus 2x. This function, I know that it is actually a nice function, such that if I want it to be continuous, I should be able to plug in. So I plug in to get k times 2 squared plus 2 times 2, which is the same as 4k. So I have 4k here, 4k plus a 4. So to find the value of k, I want this limit to be equal to the function. So I want 8 minus 2k to be equal to 4k plus a 4. And of course, I'm going to take this one here, which has a k, to the other side, and this number to the other side. So I have an 8. 8 is left there. This 4, I am jumping the equal sign, so it was positive. It has to change a sign. So I'll have minus a 4. And then this side here, I had my 4k, and I'm taking this one on the other side, so it's going to change its sign. I will end up having plus 2k. And then, of course, 8 minus 4 is going to be a 4. And then 4k plus 2k is going to be 6k, or k must be equal to 4 over 6, which is just the same as 2 over 3. That's the value of k that we need for this function to be continuous at this particular point. That's what you do. Even here, that's what you do. And I will call it a day. Hopefully, this gave you some insights on what is actually important. A little bit of what is important here. For continuity to actually happen, these are the 3 things that are important. F of a must be equal to some value L, which means that f is defined first, and if it is defined, which means is defined at x is equal to a. In other words, a must be part of the domain of f, and f of a must be equal to some value L. That's what is important here for this function to be continuous at that point. And then secondly, the limit as x approaches a on the left of f of x, it must be equal to the limit as x approaches a on the right of f of x. So the limit must exist. This is what is important. Limit must exist. And then the last one is the limit as x approaches a on both sides of f of x must also be equal to L. In other words, it must be equal to f of a. That's what is important. So this is continuity at a point. And the second one, on the interval, what we're actually saying is that function is continuous on this interval if whenever I am taking the limit as x approaches, if this is the interval AB, the limit as x approaches a on the right of f of x must be equal to f of a. And then secondly, the limit as x approaches a on the left of on the left of b of f of x, it must be equal to f of b. And more importantly, whenever I pick another point a, x approaches some k of f of x, it must be equal to f of k, where k is an element in that interval AB. So those are the conditions for the interval. That's all there is to this thing. And we also have point of discontinuities, where we have a jump discontinuity, removable discontinuity, and at infinity we actually also have a discontinuity at infinity. That will be all for today.